Hi. So in this particular video, I'm going to talk to you about some of the direct metrics you can actually apply to your product. So the types of measures that you could actually apply to your product are either direct measures or indirect measures. Direct measures talk to the internal attributes of the product, whereas indirect measures talk to the external attributes. So for example, for direct measures, you have things such as the cost of the product, the effort, the number of lines of code, the speed of the software, the memory that it actually takes up. For the indirect measures, you talk to things like the functionality, the quality, complexity, efficiency, reliability, and maintainability. The first kind of metric that you want to be able to measure, probably the simplest one, is talking to the size of the software that is produced. These are the LOC measures, so the number of lines of code, which you can directly measure out your program. The next is the kiloloc, which is every 1,000 lines of code. Next is SLOC, which is the number of lines of code which is ignoring the white space. So some typical measures that you could use are errors per kiloloc, defects per kiloloc, cost per loc, the documentation pages per kiloloc. This might be document pages that you have in a document somewhere, or it could be even say the number of comment lines per kiloloc, for example. So LOC metrics are actually very easy to use and very easy to compute, because they're just written off the edge of your source files. However, they tend to be very language and programmer dependent. One programmer going from using the same programming language as another can write perhaps the software in a shorter, more efficient way than another, and going from one language to another where there's actually more libraries and more features, it might be easier to write it. So you can't really compare in any meaningful way using LOC metrics if you're moving from one language to the other, and it's very hard to kind of discern between one programmer and another just off these kind of direct values. So we get to the next set of metrics, which are the complexity metrics as opposed to the size oriented ones. LOC is actually just a function of these complexity metrics, and complexity metrics are still language and programmer dependent. The first complexity metrics that I'll take you through is by a guy named Halstead, where he measures first these things which are the distinct operators, distinct operands of your program. So the best way to explain this is using an example. So see here we have this little piece of code which is just two nested if statements using variables k and x. So first thing we want to do is we want to just count up the number of distinct operators and the number of distinct operands. So the distinct operators are things like if, open regular bracket, open curly brackets, greater than sign, less than sign, etc. The operators are k, the number 2, the number 3, x, and you have that in program. So repeating that n1 and n2 has to do with the number of distinct operators and operands respectively. If we just count up the number of these, you get 10 and 4. And then the big N1 and big N2 have to do with the total number of these kinds of things. So with the distinct operators, you would recognize that the if statement is repeated, and the open regular brackets are also repeated in this little program. So you actually get 13 for those operators, and also the k is repeated 3 times and the x is repeated twice, so therefore you get the total number of operands as being 7. And that's the quick Halstead basic measures. So now we actually going to talk about the metrics that we're going to actually use these little measures that we've made to talk about different things about this program. The first metric is the program length, denoted by capital N, which is just the sum of big N1 and big N2, the total number of operators and total number of operands. The program vocabulary, denoted by little n, is actually the sum of the number of distinct operators and distinct operands. The estimated length of the program, which is actually a close estimate of the length for well-structured programs, is actually given by this formula here, and is denoted by the symbol capital N with a little caret on the top. The next measure that Halstead proposes is what is known as the purity ratio, which is the ratio of the estimated length to the program length. So moving along with more of Halstead's metrics, you talk to those that have to do with the complexity of the program. So The first one is the volume of the program, which have to do with the number of bits required to provide a unique designation for each one of the items in the program vocabulary given by this formula here. The next one is the difficulty of the program. So this metric talks to how difficult it is to actually write this program, and the program effort, which is just the multiplication of v by d, which is a good measure of how understandable a program is. And the final program complexity metric that people talk about with Halstead is the time required to program something, which is equal to the effort divided by 18, and this time is in seconds. So for example, you can actually go and for a particular program, say, if you knew what his hourly rate is, or how much you would charge per hour to write a piece of program, and you knew how much you're going to pay your programmer, you could actually use this metric to compute the time it would take them to write a piece of code that they wrote, and you would be able to use that to actually compute, say, the cost for writing that particular piece of program. Okay, so other than Halstead, for complexity measures, you also have another guy named McCabe. So McCabe metrics are based on control flow representation of the program, and we're going to do a bit of graphing for this. So we are going to have like nodes and edges. So nodes represent the processing task, where there are one or more code statements, and the edges represent the control flow between the nodes. So if you have a sequence, it looks something like this, where you have there's one statement leading into another statement leading another statement going along. A while statement, you would note that you would have one thing, then you go and do another thing, and then you keep coming back and checking the condition over and over, and then when the condition becomes false, you move on to the end. If you have if then else, you have two potential branches. You can go into the if statements part or the else branch, and then at the end of choosing one of those two parts, you actually go and converge and do something that happens after the if else statement. And then you have things like repeat until, or you might be familiar from C++, like the do while, where you would do something, then check to see if you're done doing it, and they keep repeating that over and over, and then when that condition equates to false, you just move along and do whatever it is after the repeat until or the do while statement. So that's just a rough idea of, you could actually put take your program and put it into a kind of flow graph like this. So as a quick example, you can try working this out. For this particular program here, you could actually try and translate it and see if you could actually make a flow graph out of it. You could also bring it to me and I could take a look at it, see if you've actually translated it correctly. So you could pause the video at this slide and give that a whack. But what I would like to get into is how you actually use this to actually calculate something meaningful, and the thing that we can calculate is what is known as the cyclomatic complexity. Cyclomatic complexity gives you the set of independent paths through the graph, which is the basis set. So it's actually given by this formula here, which is E minus n plus 2p. So E is the number of flow graph edges, so that is the lines between each of the bubbles that would drawn for the flow graph. N is the number of nodes, that's the number of statement points, and P is the number of what you call the connected components. Now P, for probably all the code I will ever give you in this course, is going to be 1. P is not 1 when you have things like programs that are parallel executing, and you have multiple unconnected graphs popping up. So you see the idea of connected components. You have like one connected graph and another connected graph. So then P would be 2 for things like that. So you have two parallel kind of flows happening at the same time. For this course, I think it's safe to assume that P will be 1. So here's an example of a flow graph going from 1 to 2 to 3 that someone would have drawn. And for this particular flow graph, we can compute VG. So let's see if you could actually come up with the same numbers that I came up with here. so you give the video a pause. Here we can count up. We have actually 7 nodes, and we have 9 edges between those nodes if you count up the arrows. So that VG becomes 9 minus 7 plus 2, which is 4. There's another formula for VG, but I'm not actually going to use that. It's actually P plus 1, where P is actually number of endpoints. I'm refraining from using that in this particular course. So the idea is that coming out of this cyclomatic complexity number, which we found out is 4, that means that there are 4 different paths that we can use to actually go through this particular flow graph. And those 4 different sets are given by these 4 flows. So we could actually go from 1 to 7 and then we're done, or we could go 1 to 6, 1, 7. Oops, sorry. 1 to 6, 1, 7. So you see, these are the 4 different ways that we could actually go through. So computing VG is useful for when you're actually doing path testing, to actually establish the minimum number of paths that your graph can be traversed, your program can be traversed in order to actually path test this thing. So we know we have to come up with four basis set paths for this program. So here's another example. I want you to give this a try. I could pause the video at this point, where you can actually try to compute this, and we could actually do this in class if you so desire, if you think you can get the answer to it. It's pretty straightforward, don't worry. Alright, so the meaning of VG, which is the cyclomatic complexity number, is the number of enclosed regions or areas in the planar graph. And those number of regions actually increase with the number of decision paths and loops. It is a quantitative measure of how difficult it is to test, and it's also an indication of ultimate reliability. Experimental data shows the value of VG should be no more than 10. Testing tends to become difficult above that value. And I think that's it. I'll talk about for cyclomatic complexity. In another video, I'm just going to mention this. For large programs, it's kind of difficult to actually compute this by hand. While you can understand how it is computed for small programs, it becomes unwieldy to do this for large programs. So therefore, they actually have a lot of automated tools which you can actually send your source code through, and it will actually give you back the number. Those tools I'll leave to another video. The next complexity metrics is that of McClure's, which is just the sum of C and V, where C is the number of comparisons in the module and V is the number of control variables referenced in the module. And this gives you an idea of the decisional complexity, so how many decisions you might have to make in your program. This is similar to McCabe, but with regard mostly to control variables. And that actually brings me to the end of this particular video. I know I hit with a lot of information on this one because there are a lot of different ways you can measure programs directly. These are some simple measures. There are others, but for the purposes of this course, these are the ones that we are interested in. So I think that's it for this particular video. See you in the next one. Bye.